Good afternoon, everyone. Welcome back to the IoT mini-conf. My name's Ben. I'm a developer at Reposit Power, and it's my great pleasure to introduce my colleague and Reposit Power's international man of mystery, Mike Leonard, hailing from the boroughs of London or Southampton or somewhere like that. So weekdays, you'll find Mike working for Reposit Power, doing a lot of programming in Python. Weekends, you'll find him riding the mean streets of Canberra on his Harley Davidson. And he's been given the coveted directly after lunch time slot to talk to us and entertain us and inform us about the messaging of things. So I'll hand over to Mike.
Thank you very much, Ben. I thought it was actually going to be worse than that. I think I got off lightly. So I'm here today to talk about messaging of things. To start off, there's a picture of me, so you know I'm not an imposter. And I'm channeling the power of Python there. I work for a company called Reposit Power. We're an Internet of Things sort of company with an Internet of Things device, and we collect a bunch of data. And that kind of forms the base of this talk. And there's my Twitter, so you can tell me all the things I got wrong. So I'm going to quickly talk about sort of three kind of areas. One is about a sort of messaging of things, so sending data backwards and forwards in the context of collecting data from like an edge device. So I'm going to talk about how we transfer that data, so some sort of protocols to use, ways we can serialize that data to try and save bytes on the wire, and kind of performance. Now performance is kind of a tricky one, where we're comparing different standards rather than different implementations of libraries. There's different devices you can run it on. Trying to compare sort of actual speed of things is going to be really difficult, so we're going to focus mainly on size of packets being sent and how robust these different things are as well. So there's a whole bunch of different serialization formats and protocols you can use to send data. The choice is almost endless, especially when you sort of think of the combinations you can use of protocols and serialization formats together. And it'll be pretty hard to figure out what you should use, where you should use it, and what's best for your application. So throughout this sort of presentation, we're going to do a simple example where we're kind of the hello world almost of like a data collection device, where we've got sort of a sensor that can collect temperature and humidity, and we want to know when this reading was taken and sort of report it back to a server somewhere. And we'll compare how we can send this data backwards and forwards. So the first thing I want to talk about is how size does matter. When we're talking about lots of devices on the internet, size does matter, and especially when they're connected to consumer home Wi-Fi, which is typically quite flaky. Might be online, offline. You could be busy streaming your favorite show on Netflix, so there's no bandwidth to upload your precious humidity data. So if we start with something pretty much everyone is familiar with, so start with JSON. So here we've got a pretty basic example of how we might send this data using JSON. There's a timestamp in there, and sort of Unix time. There's what the temperature reading is and what the humidity reading is. And we start off there as like a basic benchmark with 65 bytes. And 65 bytes seems pretty small for sending this data. It seems great. When you start putting it in the context of the Internet of Things, let's say we wanted to get kind of real-time data collection on this stuff, so we want to read once a second. That's sort of 86,000 times a day. That gives you 5.5 meg a day. You scale it up to a month, you're looking at sort of 170 meg a month. But you probably don't want just one device. As like maybe an organization or a company, you want to collect from tens of thousands of devices. So suddenly your data center, even though you're sending these tiny packets, needs to start taking in sort of like tens of gigabytes of data. Or perhaps you have multiple sensors in your home, you start getting to significant size as well. And again, half a gig might not seem that much. But if you're thinking about these Internet of Things devices, perhaps using a 3G or 4G connection, it starts getting expensive sending this sort of data. This is a really trivial example with sort of the smallest amount of data we can send, and just a tiny device. So if you scale this up to something more complicated, more devices, these numbers really start mattering quite quickly. So what can we do to this JSON to make it better? So just focus on the basics. We could take the white space out. It's a pretty simple starting point, and we shave some bytes off. So there's a good start. We could think well about abbreviating some of the stuff to take out full words that we're sending every time to maybe put in T or H. But then we've got the problem of what if we have another reading which also starts with a T? Do we go T2, something else? Do we start getting cryptic messages in our JSON, starts perhaps being not the easiest format to follow. But we can get that down to 35 bytes. And so what we'll do is we'll take this as our kind of minimal JSON structure that we can send. It's kind of the best we can do. And so we use this 35 bytes as our benchmark going forward through this presentation. So next up, we can look at other serialization formats. So these tend to be slightly more complicated to use, but they have additional benefits in the fact they're perhaps binary serialization. You don't need to have so much kind of boilerplate in the serialization itself, such as the brackets and things. So one such format is Avro by Apache. This is a binary serialization format. And to use this, you define a schema. So this is what an Avro schema looks like. We kind of give it some name information at the top. And then inside that, we define what the fields are inside this serialized format. So we've got the timestamp, we've got the temperature and the humidity. We can define the types there as well. So that's kind of another benefit over JSON straight away. We can have more complex types in there. You can do unions of types as well, because you can say it could be like a float or an int, whether or not it's nullable, that type of thing. And all these field names and stuff are defined in the schema itself, rather than the actual serialized data we're sending forward. So when you kind of serialize that, you end up with something that looks horrendous like this, with some binary stuff in there. But the interesting thing to note here is that the prefix of this message includes the schema itself, which we'll come back to later. But so with the schema itself and encoding that same bit of data, we're at 281 bytes, which is significantly worse than our JSON we had earlier at 35 bytes. But the nice thing about this is we can enhance this further, so we can batch our readings. So if we wanted to send each reading at a time, we're going to be looking at sort of 35 bytes with the JSON format, or with this format, we're looking at 280 or whatever it was. But if we batch these into a single reading, we can save some of that boilerplate, especially with Avro. We can include the schema once at the beginning, and then include 10, 100, whatever type readings in there. So we take sort of our 10 readings, and if we take an example of 10 readings inside the schema, and batch them up, we get sort of 400 bytes payload. We take off the initial part of the schema in the first reading, we get down to about 13 bytes per reading after that. So once you get past that initial overhead, this gets quite small, and it's significantly better than our 35 bytes of JSON. But I think we can improve on that still. So what if we do, so with Avro, the way Avro encodes integers, they're in a variable number of bytes. So the timestamps are obviously quite large. So rather than including each timestamp in a batch message, we include a starting timestamp and then an offset from that, which take 1 byte each. And if we do that and put that in there, and we sort of add several messages to the payload, we start getting down to about 9 bytes per message. So now we start getting a lot smaller, and we haven't done too much here to really reduce the payload size and be able to send far more data as we're collecting things. So Avro has Python libraries, and it's pretty straightforward to use. You define your schema in a Avro schema file, and then there's different options. So here's an option for reading that schema in, and then writing some data to a file using that schema. And it's pretty straightforward, just a few lines of Python there. Some other languages do have code generation tools for Avro as well, to sort of generate objects from your schema to use, but unfortunately the Python library doesn't. So next thing, which is also becoming quite popular, is protocol buffers, which is a very similar concept to Avro. It's a serialization format, binary serialization format, but it has kind of a different approach to things. So similarly to Avro, it has a schema format, which is what we can see here. Some basic introduction stuff, and then kind of the message format beneath that. Again, we've got types in there, and the field names. Difference with protobuf, which we'll come to a bit later, is that the fields in protobuf are tagged. So these numbers here identify, need to be static, identify the bit of data you're encoding. So protocol buffers have really good code generation tools. So with this, you basically take your input proto file like we just saw. We run a command line command, and it spits out essentially a Python library specific to that schema. And then from there, you can treat it like a sort of plain Python object. You can import it. So this proto environment PB2 is the generated code. And then within that, we can create an environment object. We can set the timestamp for the temperature, humidity, and then we can just serialize it to a string. And with that, we get something that's about 9 bytes straight off the bat. So slightly better than the average schema to start with. And with the protocol buffers, you don't have to send the schema. So trying to go on what we looked at before, we can try and do multiple messages in a single batch. So to try and do this, I created a message type. So this is the sort of record, this top bit. And then you can basically say this reading is repeated several times. Interestingly, this actually quite significantly increased the payload size per record. I think it's probably due to the complexity of defining the type like that and having to have it mapped back. So I don't know quite why that is. But that significantly increased it. But there's no reason why you can't just send lots of messages for this format. Similarly, I did the same thing with Avro, where I had a starting timestamp and an offset, and that did reduce it down a bit to 14 bytes, but still not quite as good as the initial 9 bytes we had for just straight up protocol buffer with one record in it. So now moving on to sort of protocols. So now we've seen how we can serialize the data. We've seen how we can have savings in there either just by perhaps taking some shortcuts in the JSON, so trying to reduce the payload size by putting in abbreviations, or using something like Avro, which is binary serialization, and putting multiple things in there. Now, once we've serialized that data as small as we can, how can we send it in the most efficient way possible? So probably going back to basics again. So probably the most common way to think of would just be making an HTTP post request. We've got some data, we've got some JSON, we can send that. So back to that same original example, this was 35 bytes to start with. By the time we add the overhead of the request headers, in this example here, which is pretty common, you'd see we've got the host, the content type, we're now at 112 bytes. So we sort of tripled that message size just with the HTTP headers, which have to be then kind of fixed. So this got me thinking, how can we reduce the header size in a regular HTTP? What's the bare minimum we can have? Turns out with HTTP 1, you can have just the post part. With HTTP 1.1, which is pretty commonly used, it's been around since 1997, you must have a mandatory host header. But I was wondering how mandatory that actually was. So I tried removing it to see what happened. And with Nginx, by default, I don't know if you can change this, but Nginx by default, if you don't include the host header, it will give you a bad request. And that curl at the bottom there, I'm stripping the host header out, and it comes back with a bad request. And I'd imagine that probably quite a lot of people in this room, if they're doing web servers, are sitting it behind Nginx. So really, you're gonna be stuck with those two headers at least, which is a large overhead for the amount of data you're sending. So that brings us to HTTP 2. So HTTP 2 is kind of the history is from Google originally created a protocol called Speedy, SPDY, which is kind of an experiment, and it was enabled in the Chrome browser only. And that kind of went on to form the basis of the HTTP 2 spec, and Speedy is now deprecated and gone from Chrome. The idea of HTTP 2 is it basically works the same, but it changes the way the data is sent on the wire and what the browsers do with it to offer improvements. And there's some additional features in there as well. So it does multiplexing, and there's a feature called server push. Server push is basically you can make one request, and the server can decide to give you multiple things back. So for example, if you requested sort of a home page, and that home page you knew you needed CSS and JavaScript and stuff, it can push those things to you as well to save the overhead of making additional connections and waiting for that round trip to request the next resources. But probably the most interesting thing in context of messaging of things is header compression, which is a new thing in HTTP 2, which compresses the headers to try and reduce their size. And it uses an algorithm called HPAC. Here was a kind of fun example I saw of HTTP 1 versus 2, where in HTTP 1 you have to pass all the ingredients individually, whereas in HTTP 2, if you want a meal, you can just have it all in one go. So with HPAC, how does it work? So kind of the most fundamental part of HPAC is it uses a static dictionary to look up commonly used headers, and in some cases, they're commonly used values as well. So there's sort of, I think maybe 100-ish different values in the static dictionary as part of the spec. And some of those include the values. So you can see status codes, for example, is very, very common status codes we use. They live in this dictionary. So if a header lives in the dictionary, either just the header name or the header and the value, that can be encoded in the header of the HTTP request as just 1 or 2 bytes, rather than sort of a byte per character, as it usually would be. So we can save masses of spaces there. Also, the servers and clients can build up dynamic dictionaries. So sort of as requests go backwards and forwards, they can come up with dictionaries specific to those requests to try and compress further. And so these can really save a massive amount of space. And I've kind of got an example here. I don't know how well you can see it, but there's 2 equivalent requests, one against an HTTP 1 server and one against an HTTP 2 server. You can kind of see they've got all the same data being sent in the response, 36 bytes. They've got the same sort of headers. But if we take a look at the size on the Y here, so this is just a screenshot from Chrome DevTools. The top one is HTTP 1, the bottom HTTP 2. And the size figures on the right, the black number is kind of size on the wire, so what was actually transferred. So it takes into account the headers and things, takes into account any like gzip compression you have. But specifically here, you can see for the HTTP 1 request, it's 134 bytes for the 36-byte payload. And for HTTP 2, it was just 58 bytes for the 36-byte payload. So they're completely equivalent, but significantly smaller for HTTP 2. And that's mostly to do with the HPAC header compression. To see an example here, here's basically most of the request headers that were sent. If we take a look at those, we can actually see that all the ones there in white, they can all be compressed to just pretty much just 1 byte each, which is a pretty significant saving. You don't really have to do much to achieve that if you're using HTTP 2. So the next thing we'll talk about is MQTT. So this has been touched upon this morning. So MQTT is a reasonably old standard for messaging developed by IBM. It stands for Message Queue Telemetry Transport, but interestingly, it's not actually a queue. I think it came out of a suite of tools that were branded like that, but it's not actually a queue. It's designed to be super lightweight for devices with either low power CPU or in restricted environments where they've got low bandwidth connections. It's a pub sub-architecture, which I'll show you a diagram of in a second. It's really quite a simple protocol. You can sort of read through the spec, and there's not much to it. And you kind of use these methods in there to say you want to connect to a message broker, disconnect, publish a message, that sort of thing. And they also have some settings in there for defining quality of service to ensure message delivery. So for those of you that don't know about the pub sub sort of model, the general idea is this temperature sensor on the left here could be a edge node device. HiveMQ in the middle is a MQTT broker you can get. Basically, messages get sent to that broker, and then things that want to do something with that message, either display it, process it, store it in a database, whatever, they subscribe to the broker, and we use topics. So you might say a topic like this. So you might identify where the data's coming from, so like an address, for example. You say it's a bedroom, and we're getting the environment data. So each time a device publishes some data, it publishes it on this topic. That goes to the broker. And then servers or other devices or web apps or whatever that want to read that data, they subscribe to the same topic, and each time a message comes in, they get notified. You can do some nice stuff in there as well with sort of wildcardy things. So the plus means match one level here, no matter what it is, and the hash means match any number of levels and subscribe to all those things. Now, the nice thing about MQTT, when we're talking about message size, is that the headers compared to HTTP are tiny. The fixed headers of an MQTT packet are just 2 bytes in size. These define the type of method we're sending, so if it's connect, disconnect, publish. And they also define some flags specific to sort of quality of service, whether this is a repeat message, some basic stuff like that. The second byte just tells it how big the rest of the message is. So MQTT doesn't necessarily define what you send. Kind of like HTTP, you can send binary, you can serialize some format, JSON, whatever you want. So you tell it how big the rest of the payload is you're sending. And then depending on the specific message, there might be a few other little headers you need, such as the topic name, that sort of thing. But given that the fixed header with every message is 2 bytes, that adds very, very little overhead to whatever it is you're actually sending. So you can do MQTT in MicroPython as well as Python. And kind of the gist of it is you create a client, you connect, and you publish a message. It's really quite simple to use. Those headers are added on for you. So another couple of things I want to talk about quickly are WebSockets for one. So WebSockets are great because there's basically no overhead. Once you've got the connection there, there's a TCP stack, but beyond that, there's no additional headers that sort of you typically send backwards and forwards, which is nice. The bad thing is it means there's no topic type information to indicate what you're sending a message for or anything like that. So you're going to have to connect in such a way or send something with each message. One interesting thing you can do is you can actually use sort of from a browser or something, you can do MQTT over WebSockets. So you can have all the power of MQTT like in a browser or something. So if you're building a solution that uses MQTT, you can use that same technology to power the data being delivered to your browser. And then whether it's good for the Internet of Things, plain WebSockets, I'm not super sure. Like you kind of got to have the full, if you've got a small device, you've got to have the full TCP stack and kind of a WebSocket stack running there. I think things like MQTT or even just using straight up HTTP, if you can have that overhead of the bytes and the header is probably a better solution. Another thing I think that's interesting, but perhaps not a great application for Internet of Things is gRPC. So this is getting quite popular. But I think it's more for sort of server-to-server communication. So I won't talk too much about that. So I just want to talk quickly about robustness as well. So it's all very good being able to have super tiny packets, use these super light protocols, send messages backwards and forwards. But it's no good if you can't actually get the messages you expect to get, or if parts of them are corrupt, that sort of thing. So one of these things about being robust is to try and use a serialization format rather than just sending JSON. If we can use something like Avro or Protobuf or some of the other ones out there like Thrift, then you can kind of have better guarantees about what data is going into that packet. Both ends have kind of agreed upon a format already, so you know what to expect. But also you can have richer data types in there, so you can define better data types, a union of data types, whether or not something's nullable, that sort of stuff. But with this, there comes the complication in that because both these parties have agreed on the schema format, what happens if we want to change it? And especially in the Internet of Things, if we've got thousands of devices out there, if we make a change to it, how do we push that update out to all the devices? Perhaps some of them have received an update and other ones haven't, and we could be quite far behind. We need to deal with that. So Protobuf deals with this reasonably well. The gist of Protobuf and how it serializes, it basically just concatenates all the fields together in a big long list, and there's a byte before each field indicating which tag it is. We just already saw those 1, 2, 3 sort of tags beforehand. If a field is marked as optional, it's simply omitted from the message entirely. So it doesn't matter in retrieving things. And because fields are tagged, we can rename them quite happily. So what this means is we can change the schema format quite easily, so long as we always tag things. So the optional and required type fields, required meant they always had to be present. And in Proto 3, that's actually been dropped because it was seen as being almost impossible to maintain backwards compatibility. If something was once marked as required, it must always be marked as required. So that's gone now in favor of doing sort of softer validations in your own logic. So you can, and because everything's tagged, we can quite happily add and remove fields. And if it gets to a tag it doesn't understand, it would basically just skip it. And we can mark new fields we add in as optional, so that older things that are serialized with that item in there, they can just ignore it. Avro does things quite differently. So the way Avro kind of works is Avro you can give a read and a write schema. So you can tell it what schema this data was written with and what schema you should read this data with. And that's partly why in the example I showed earlier, I included the schema as part of that initial message, so that when the reader picks it up, it knows exactly what version the schema was written with. Now that's not the only way of doing it. You could tag the data in some way to say this is written with this schema. Or you could perhaps, if you're using MQTT, you could perhaps connect initially and then kind of agree on the schema you're using and do things rather than sending it with every message. But Avro does some really smart stuff. If you do provide a read and write schema, Avro can do some really smart stuff to figure out kind of precedence in there and figure out what field should be. And because it's got both schemas in there as well, you can do reorder fields and stuff, and you can rename them to some extent, and it'll kind of figure them out for you. You can also rename fields and supply an alias to them, which means that you can say it used to be called this name. So this gives you quite a lot of flexibility over being able to modify that schema and still have devices out there using a slightly different version, an outdated version, and still read the data you've got. And sort of finally, the last thing I want to talk about in robustness is MQTT's quality of service. So something you can specify and build as part of the spec, and most of the libraries implement, is this idea of quality of service. And when you send a message, you can basically say if you want it to be delivered at most once, at least once, or exactly once. Each one of these kind of has additional overhead, but the specification around how this works is pretty straightforward, and there's just some messages backwards and forwards to kind of ensure these things. So if you can couple a serialization format with something like MQTT, where you can do guaranteed message delivery, you can really start reducing that payload size. You can ensure the quality of the data you're sending. You can be backward compatible, and it all works really well. So just kind of to sum up, what I wanted to the point I want to get across was when we're sending messages on the Internet of Things, and we're sending a lot of volume, it's really easy to just serialize a JSON, send it as an HTTP request, which is fine. It works. Everyone's familiar with it. Pretty much every device can do it. But you can very, very quickly get to massive amounts of bandwidth without even realizing, be that either on the device itself and some consumer's home Wi-Fi, or the fact you as a company need to support tens of thousands of devices, and all those little bits of data added together can form massive gigabytes of data. So really think about the message format in terms of how you're representing it. Can you get some wins by batching things up and sending them occasionally to minimize overhead? Can you use a serialization format to reduce it down even further? And then think about the protocol you're using. HTTP comes with a reasonable amount of overhead. Can you use something else? Do you need to have that additional sort of quality of service guarantees like MQTT offers? And then the final thing I had in here was plan for scale or plan to fail. Just simply, the idea of the Internet of Things is not one device. There's meant to be millions of them. You really need to plan for that kind of scale, or things aren't going to work. That was it. Thank you very much.
Do we have any questions?
Just one thing about security. So AWS, for example, you can connect to their IoT platform, but you have to have certificates and stuff. So what's been your experience with getting that up and running, or do you think it's important? Not important?
It's definitely important. I don't have much personal experience in doing it with some of these things. Most of this stuff is based off research rather than a production environment. But there's a variety of ways of doing things that will, again, incur all their own overhead. So I think the important thing here is just consider what you want to do. Like, do these benchmarks, kind of figure out how long things take, what the packet size is, do you have massive overhead, and how can you reduce those things? So if you do have, exchanges of keys, or you need to connect in some way, can you do that once up front and then send lots of messages rather than having to do this connection and kind of do this each time?
It was essentially the same question. Some of them protocols use HTTP headers to have the keys in there. Don't know if will be able to HTTP2 will be able to encode that.
The dictionary probably won't encode it, but like the HTTP2 essentially works exactly the same way as far as you're concerned. If you can put something into a header in HTTP1, you can do that. And I believe the dynamic dictionary. So if you're sending the same sort of authentication. So the authorization header, the key part of that is in the dictionary, so it can encode that. But I believe the value part could potentially form part of this dynamic dictionary that can build up.
Okay. All right. Take one last.
Hi. So you've mentioned serialization formats a bit and binary serialization formats, but I know in my personal experience, sometimes it's really handy just to be able to say open up Wireshark and start logging raw packets if you're a bit suspicious of the data coming in. So do you have sort of an opinion on that, ease to debug versus small data?
Yeah, it is harder to debug. There are some tools out there where you can get some, I don't remember which one it is, but there's some plugins you can get for Wireshark, I believe, which with some of these protocols, you can actually decode them in Wireshark. So for the most part, you can just treat it as if you would any other thing over HTTP.
Thanks, Mike, for the talk. Here's your obligatory mug. If you find it go missing from the break room, it probably wasn't me. So.
Cheers.